Hello everyone, my name is Linjie. I come from Institute of Software, Chinese Academy of Sciences. Now I'm going to introduce my paper, Static Asynchronous Component Misuse Detection for Android Applications. My presentation includes 5 aspects. At first, we know that Android system adopts single-thread model. The main thread only accounts for the UI update, while time-consuming or resource-blocking tasks are always packed into background threads. To simplify async programming, Android provides many async components. So, how do developers use these components? Well, to answer the question, we conducted empirical study on real-world applications. The result is shown in the table. We counted the use frequency of 6 async components on apps from 3 different repositories. F-Droid is an open source store. Google Play and Wandoujia are commercial stores. Obviously, the use frequency of thread and async task are much higher than REST components. Thread is not Android specific, so we focus on async task. Although async task is widely used, it is only appropriate for short missions. In fact, the abuse of async task can lead to many problems such as memory leak and wrong update. To solve these problems, we developed a static analysis tool called Async Checker. Well, before detecting the misuse of async task, we need to know how async task works. Async task is an abstract class. It provides 5 methods for developers. Among them, only doing background methods runs on the background thread. The other 4 methods all run on main thread. That is to say, the background thread packed operations such as downloading a music. This picture shows the interaction process between main thread and async task. To use async task, we need to define its subclass and invoke execute or execute on executor method to start a background thread. Before the background thread end starts, onPre-execute will be invoked. During the execution of doing background method, we can use onProgressUpdate to interact with main thread. After the background thread ends, onCancelled or onPostExecute will be invoked. Here, one and only one of these 2 methods can be invoked, and it depends on whether cancel is invoked when background thread is alive. Okay, that's how async task works. As I said before, the improper use of async task can cause problems. In accordance with these problems, we proposed 5 misuse patterns. We will use some examples to explain these patterns. Strong reference. Here we define an instance of async task, and it holds strong reference to activity. Now, if the async task lives longer than the activity, then the memory of activity cannot be garbage collected after it is destroyed, which causes memory leak. Second, not cancel. If we don't cancel async task before the destruction of activity and async task lives longer than activity, then onPostExecute will be invoked after the destruction of activity. In this example, there is a GUI update operation in an onPostExecute, which means we will update a non-existent GUI object, which is dangerous. Third, not terminate. In fact, cancel method can't terminate async task. To interrupt async task, we need to check whether cancel is invoked in loop structures within doing background and jump out of loop if async task is cancelled. In this example, there is no cancel check within the loop. and not terminate occurs. The rest two patterns are much easier. Early cancel means the async task is cancelled before started, which is semantically wrong. The last pattern is repeat start. It means that an instance of async task can't be started more than once, otherwise the app will crash. Let's say to detect them, we developed an analysis tool called Async Checker. This is the overview of the tool. We take APK files as input. During preprocessing, we build dummy main method for each activity and obtain class hierarchy relation. To build dummy main method, we combine the lifecycle methods of activity together. During the analysis phase, we perform type state analysis, reference analysis, and loop analysis to collect the information about async task. At last, any detected misuse will be recorded in bug reports. So before I introduced the analysis phase, I want to talk about this one, the partial interprocedural strategy, which is used during type state analysis and reference analysis. This strategy is based on an assumption. Most of the operations in apps are async task irrelevant. That's easy to understand. Developers write apps for a specific purpose, and they just use async component to help them. Async checker is path sensitive. If we unfold all invoked methods, there will be many redundant paths. Therefore, we only perform interprocedural analysis for methods that contain async task related statements. Here, async task related statements means those statements that contain async task variables. However, due to the polymorphism, it's difficult to judge which method is invoked at the call site. In order to keep precision, we first generate a list of possible invoked methods based on class hierarchy relation. Then we traverse the statements of these possible invoked methods one by one. If any of the methods in the list contains async task related statements, we take the call site as async task related one. Okay, now let's come to analysis phase. The first part of analysis is type state analysis. A type state denotes the state an object can occupy during execution. Apparently, the operations on an async task object can change its state. So we define the async task state transition model to represent the state of async task object. During analysis, if we detect the operation of async task, we change its state. If the async task object is in wrong state, then we find a misuse. Besides, type state analysis is also the basis for reference analysis. The second part is reference analysis. As the strong reference pattern shows, we need to record the mapping relation from the fields of async task to GUI objects. Such relation is built through possession operation, which is the assignment whose left operand is the field of async task, and right operand is the GUI object. The type of a GUI object is the subclass of view or activity. Here we use an example to show the mapping relation. In line 6 and line 7, we define an async task object and pass 3 arguments to it. Now it holds strong reference to GUI object through V1. Through S1, it holds strong reference to long GUI object, and through V2, it holds weak reference to the GUI object. Among them, only in the field V1 is a real strong reference, and it can pose potential memory leak. Note that weak reference or reference to non-GUI object doesn't lead to strong reference. The third part is loop analysis. We identify loop structure and detect whether its cancelled is invoked to jump out of the loop. different from type state analysis and reference analysis. We perform loop analysis in bottom-up manner while topological sort. Here, we calculate the loop sets for callees and merge them to callers until we reach doing background, the top-level caller. In this example, there are two loops within the doing background method. The first one is valid, and only the second loop lacks terminate operation. Okay, that's how we detect misuse of async task. We developed async checker based on Androlic, a static analysis framework developed by ourselves. We analyze the semantics of statements via the core engine of Androlic. Considering the characteristics of async task, we implemented some APIs of Androlic. For example, we support partial interprocedural strategy by implementing this interface. To support type state analysis, we define subclasses to denote async task object and its state. To identify async task operation, we implement this interface to process library method invocation. Async checker is totally open source. Welcome to download. To evaluate our work, we proposed 4 research questions. First, we designed a benchmark suite called Async Bench. Currently, Async Bench contains 69 apps which are divided into 6 groups. This table shows the experimental result of Async checker on the benchmark. It looks good, but not convincible enough. We still have to apply Async checker on real-world applications. We evaluate Async checker on 3 repositories as we did in empirical study. The first table shows the overall result. Here, we analyzed more than 1,000 apps. Among them, nearly 8% contains at least one misused async task instance. In the second table, we list the frequency of each misuse pattern. As we can see, the frequency of early cancel and repeat start are lower than rest patterns. It's easy to explain. On one hand, many developers don't know async tasks should be cancelled. No cancel means no early cancel. On the other hand, repeat start can directly lead to crash. Developers can easily find and fix it during testing. This picture shows the efficiency of async checker. As we can see, the average running time is totally acceptable. Where we have found many misuse of async tasks on real-world applications, we need to manually check the result. Since it's difficult to obtain the source code of commercial apps, we randomly select 22 apps from F-Droid and counted the precision, recall, and F-measure. The manual result validates our experiment. Let's come to the third question. Compared with existing tools, how does async checker perform? Here we consider 2 existing works, AP checker and DiagDroid. AP checker combines static analysis and dynamic GUI exploration. DiagDroid is based on instrumentation and random testing. We contacted the authors of these tools and obtained the source code of DiagDroid. In this part, we compared DiagDroid and async checker on 22 apps from F-Droid. As we can see, async checker can find more async issues than DiagDroid. There are 7 issues of DiagDroid that we can't assure its error types. So the bug report of async checker is friendlier than DiagDroid. Okay. Finally, the last research questions. Do developers take the misuse of async task as a problem? We report issues of 17 apps to developers of F-Droid via GitHub. 10 developers confirmed or fixed the problems found by us. From the feedback, we can conclude that developers take strong reference as the most serious pattern of async task. Okay, let's make a brief conclusion. In this paper, we summarized 5 misuse of async task, the most widely used async component in Android. Then we developed a static analysis tool called Async Checker and applied the tool on both benchmarks and real-world applications. We found that misuse of async task widely exists in real-world applications. That's all. Thank you.